Welcome to Hot Chips 18. Session 1. Video Processing.
Welcoming you, and as you're all well aware, this is a premier venue for chips, techniques, and technologies, and hopefully you will see that today. And I think we have a really strong program this year. There's 27 talks, so things are going to be tight. Maybe halfway through you'll want to raise your hand and ask to be excused because your brain is full, but just hold on. 2 days for really good talks. We've got the standard high-performance processors. Wouldn't be hot chips this year without some multi-core. We have some embedded processors, multimedia, communication chips. And we also have some interesting things like memory and disk and other uses of silicon. You should definitely come to the novel silicon session, which I think should be fun. We have two very exciting keynotes scheduled for you. One of them from Intel actually has a couple of terawatts worth of equipment in the back here that apparently is going to be doing some amazing stuff. Assuming that we don't see smoke coming out of the back behind the curtain, just ignore that if it happens. So that should be fun. We had two well-attended tutorials yesterday and got good feedback from those. And tonight we have a very good panel on who owns the living room. And I think that should be fun. So you should definitely come to that. And it's kind of continuing a theme started yesterday in tutorial number 2 about wireless in the home. So I guess at some point in the future we're going to be asking Hal to turn our oxygen back on or something. I don't know. So I wanted to say a little bit about the submission and selection process. We had a record number of submissions this year, 65 in all corners of the globe, which was quite impressive. We also had a record number of spam submissions. I'd never realized that Viagra was a hot chip, but this is probably the last year we're going to use email to submit. Probably those of you who submit next year will be seeing a web form of some sort because I had to sort through all this spam. I also wanted to say a little bit about the paper evaluation process. We don't just wait for submissions, we solicit, as you may be well aware, so that makes this conference a little bit unique. And so we make sure that the program committee has a nice mix of industrial and academic folks, and so we know who to target, and that's worked very well for us. And the submissions are just abstracts, not whole papers. Keeps hot chips on the bleeding edge, and which I think is a good thing. Hopefully you'll agree. And acceptance is provisional. What we find is that the session chairs are actually reviewing for technical content, and we actually have the option of bouncing things that don't quite meet that requirement if they're marketing, for instance. So one last thing before I go and hand over the microphone here. Audience participation. Let's not participate by crinkling our bags. They are a little bit noisier this year than normal, so be careful. And the cell phones should be watched. Questions. Try to hold the questions until the end of the talks, but then ask a lot of really good probing questions. All right, that's what makes this conference interesting, and of course you can go at break times to get more. And come to the panel. All right, good questions there will be good. Finally, fill out the evaluation forms. Those are in your bags. I think they're yellow. We really rely on these. It'd be great to actually have them. And they'll help us improve next year. And visit the table of our sponsors. And I will say let the conference begin, except that we got a little bit misordered. So I'm going to actually forward on to John Maschey for a few words here. Don't forget one when you're done there. Oh, yeah, right, okay.
Just did that. That's all you gotta do. And we're off.
Okay, great.
Hi, thanks. I'm John Massey. In this instance, acting as a trustee for the Computer History Museum. We always give me about 5 minutes to give a quick pitch here. How many people here have visited the Computer History Museum? A good fraction, but not all of you, so we got to fix that. So, our mission is to preserve the artifacts and stories from the quick rise of computing. We've existed actually for quite a few years. It used to be in digital equipment, then in Boston. In effect, it moved out here. We followed the standard Silicon Valley tradition of living in a unheated garage, or pretty close, for years at Moffett Field. In the last few years, we've been at an old Silicon Graphics building that we purchased not too many miles from here, and we keep doing new things. In particular, about a year ago, we opened a new exhibit on computer chess. So here's some of the history, and ending in the picture of where we are. One note, we're open more than we used to be. You can just walk in 4 days of the week. You can get docent tours during that period. Take a look at the website for the detailed schedules. Also make a special offer. If you think you can get up a couple people, I'll be around during a conference. Talk to me. I do docent tours, including going to some of the places you normally don't get to go. Right? So talk to me. I always love to take people around and show things and answer questions. We have an amazing collection, the biggest in the world, not just hardware, but software, ephemera like the Unix license plate, documentation, and so forth. We have a terrific collection of amazing things. My personal favorite is this thing called the Neiman Marcus kitchen computer, which has to be seen to be disbelieved. It's quite an amazing device, right? It's probably the best example of inappropriate human interface in the world, since it was made for doing recipes, but the only input was rocker switches. They sold 0. Okay, now this is what we've got and where we're going. We have a lot of things in what we call visible storage, which has a lot of interesting artifacts and reasonable signs, but is not a professional, interactive, audio-visual type display. We've done one of those, which is an exhibit on the history of computers and chess, and that's open and you can see that. We'll have multiple theme rooms like that, and we're especially working hard right now, for a few years off, is a major computing history timeline, and in particular, we thank Bill and Melinda Gates for giving us a bunch of money to do that. And we'll have a lot more. We have a fair amount of space down there, and we're going to take a lot of the stuff in storage and turn them into exhibits. Here's a quick thing about the computer chess exhibit. This one was an interesting challenge because it's got software, chips, hardware, histories of people. Is a lot richer sort of exhibit than just showing you a box or a chip. Very important, we're not just the physical museum, we are a cyber museum as well. A lot of what we do, we make sure we put online. Behind the scenes, and this is one of the places I'll take you if you choose to come to a docent tour, is an amazing collection of stuff, right, from computing history, and certain very famous people have been known to go and dig around in there and exclaim over putting BASIC on an Altair machine and stuff like that. We do all kinds of things. We have a long, interesting set of speakers. We, of course, preserve things, not just the physical artifacts, but oral histories. We restore old computers. We certainly do the Cyber Museum, and then we have all sorts of other kinds of events. Here are a few of the recent talks that we've had. As you can see, there's a pretty good variety, anything from Moore's Law to Shockley Semi, Sun founders, and lots of other topics. Now, people are what really matter. We get a terrific number of volunteers. Although there is a substantial professional staff at the museum, a lot of things depend on volunteers. We, of course, are fortunate to have lots of good leadership over the years. Good computer architecture guy is Len Shustek. Len, raise your hand. Right, Len is sort of the instigator of this museum and the chairman of the board. I guess will you be around? You'll be around. You should talk to Len about this or talk to me if you want to do something. In particular, one of the things that's come up lately is the Semiconductor Special Interest Group. Now, what this is doing is having a special interest group just on semis, just like we have for storage and software, because this is Silicon Valley. We have to have something to focus on this. So people working on timelines, gathering histories, worrying about what things we want to collect before they get lost. Important things, startlingly easy to get lost. We've got to watch that. Here are a bunch of the people in the different areas. If there's areas you are interested in or can contribute, please contact us. And the way you do that is email or phone David Laws at the museum. Right? So there is a mechanism if you want to get involved and you're a semi person to do this. The last other thing is stop at our desk outside. There are very cool timeline posters that you can buy or get if you sign up. Anyway, thanks a lot and come on out and see us.
So we'll get started in 1 or 2 minutes here as I load the presentation. Just a little how many of you are from out of town here? International? Oh, quite a few. Good. So we'll get started shortly.
Just a second. Ask how many have been here before.
And one more thing. How many of you have been here before? Repeat conference. Oh, quite a few. Good. So, welcome to Hot Chips 18. My name is Yusuf Abdul Ghani, and I'm the General Chair of the conference. So this year, we have more than 500 attendees attending the conference from representing more than 200 organizations. And they come from 15 different countries. So I'm not sure if this is a record or not, but this is really good numbers. We have a diverse set of people here attending the conference. The program committee has done a fantastic job of coming up with the program. You just heard Kubi talk about it. We've had 2 tutorials which were done yesterday. One was on programming for the multi-core, and the other one was on wireless and at home, challenges and opportunities. It was really well attended. More than 250 people signed up for the tutorials, and it was really well taken. Today and tomorrow, you will attend 27 presentations in 9 different sessions. There are 2 keynotes, one in the afternoon today, and the other one on Tuesday. And finally, we have 1 panel discussion, who owns the living room, this evening around 7 o'clock. So in the past several years, we have worked really hard in order to make your experience flawless at the conference. We have a new website in the last 3 years, and we've got a really good feedback on the website. There were some comments, and we have tried to incorporate as much comments as possible in the website. We have a new archive section, so that means all the PDFs, we have converted all the previous year proceedings and tutorials into PDFs, and now you can download those PDFs for free and then and check them out. Oh, thank you. By the way, it goes all the way back to Hot Chips 1, and it's really interesting to see what kind of papers were presented at that time. 3 years ago, we introduced online registration, and it has been a real success. It has made our lives easier, and it has made your lives easier as well. So we've been innovating in the past few years in order to make this conference work seamlessly. So what have we done this year? Well, this year we are venturing into new technology, and we are going to make DVDs of the entire conference. And this is how we are going to sell them. So we are going to have 3 sets, the complete Hot Chips 18 DVD collection. And then if you're not interested in buying the entire conference, then you can just get the tutorials. The complete collection contains the conference CD, both the tutorials, the 2 keynotes, panel discussion, and all the presentations. And the conference CD is actually a CD which has updated PDFs versions of everything in black and white and in color. So you can have a reference for that. You can print it and watch along with the DVD. The DVD collection has got 14 DVDs and 1 CD, and the tutorial DVD set have 2 DVDs and 1 CD. So we are planning to ship this in the 3rd week of September 2006 because we require some time for post-processing and stuff. And this is the price. The complete DVD collection is for $1,000, and if you're interested in getting the tutorials, it is $200 each. So, but if you order before September 22nd and pre-order, you get a 15% discount. So that's a pretty hefty discount. And if you are from education, we have got special pricing for you, 50% off of the entire of the regular price. If you want to order it, you can order it online via our store at hotchips.org, HC18-store.htm. And this is a pilot program. We are doing this for the first time. We don't know how it's going to work. We have spent a lot of resources at it, and we need your feedback. So if you have any feedback regarding the price, the quality, what should be done, what should not be done, what worked, what didn't work, please give us the feedback in the feedback forms that you have, and let us know what to do. So having said that, let's talk about some housekeeping stuff. There's free wireless access for you. You can connect via MEMOD-1, 2, or 3. Please turn off your cell phones. Again, I mean, Kubi has gone over it, but doesn't hurt going over it one more time. People who are interested in working with their laptops when the presentations are going on, and there are rows R, S, and T right below the balcony where there are power strips. So you can use those rows to hook up your laptops and charge them. Avoid seating in the last 5 rows of the center aisle. We have the video recording people there, and they need immediate access to the aisles. So please avoid seating in the last few rows of the center aisle. Food is in Dorman Grove, which is right across the Memorial Auditorium. And those of you who are out of town, who are visiting Stanford for the first time, the Stanford Visitor Center is right here in the lobby, and they have got walking tours and a lot of information about the university itself. So you can make use of that. Give us your feedback one more time. And thank you, sponsors. This year, Philips, Intel, Xilinx, Circuit Cellar, Fulcrum Microsystems, and MIPS Technologies have sponsored the Hot Chips. It's been an honor to get their sponsorship. And so let's begin. So welcome to Hot Chips one more time. And before I ask Howard to come here and introduce this session, I would like to thank all the volunteers, the organizing committee, and the program committee. And I hope you will enjoy the presentations and you will have a productive Hot Chips 18 conference. Thank you.
First speaker is Ben Pronk, with Philips, obviously. And he graduated with a degree in physics from the Technical University of Delft. He worked at the University of Leiden doing solid-state physics research, and later joined Philips Medical Systems doing in the magnetic resonance department, and is the lead architect in the development of system architectures for new generation of medical diagnostic devices. He's now at Philips Semiconductor as a system architect for digital television systems. Ben?
Good morning. Can you hear me? Okay, good morning, ladies and gentlemen, and thank you, Howard. Yeah, the affiliation still reads correctly Philips, Semi, but probably Semi-Philips would be more appropriate by now. As you all know, we will be an independent company very soon, and in about 2 weeks' time, I believe, we'll get a new identity. So colors and fonts will change profoundly, however. The content will stay the same, and today I want to take you into the design of one of our latest devices, the PNX8535, which is an integrated hybrid television processor. Before I actually dwell into the technical details, I'll start by giving you some context on the markets and the products in which we actually apply this device. I understand all of you are engineers, so we'll have an allergy against lengthy marketing presentations and over-engineered PowerPoints. So I'll keep that short, so that very soon we can dive into the technical details, the hot news, so to say. And I will do that guided by the agenda that you see behind me, projected behind me now, yes. It's actually already indicates some first pictures. The application background, I already told that, and then we'll dive into the actual design of the PNX8535. I'll give you an overview of its functionality and use cases, augmented with some block diagrams of the device, trying to explain you in somewhat more detail in the time given by me, and Howard has already threatened me that after 20 minutes he will come up here, so I have to hurry. So giving you some more insight in its design, and then I will focus specifically on the video processing capabilities, which are extremely key for a television processor. I'll say something about the physical design of the device. This is a true device. It does exist, so it's more than a marketing story, and it's more than PowerPoint, so it's not more than fair, I think, to share with you some of its physical data, including a floor plan, to show you that it's really there. Tell you something about all the software that we have to support with this device, and then hopefully in about 20-25 minutes that will bring us to the shared conclusion that this is not only one of our latest, but also one of our greatest devices. Okay, of course, sorry for my colleagues that come after me. Okay, some first pictures. This is a real existing IC. It has seen silicon already a number of months ago, and actually at this very moment, the second silicon is going through our fab in Crolles in France. On the market that we applied this device in, that's the hybrid television market. And hybrid television means it's a television that is able to receive both classical analog, PAL, NTSC, and all its worldwide variants, as well as digital broadcasts like DVB for Europe, as well as ATSC for the American market. Our new product, the TV520, of which the PNX8535 is the central processor, is actually the next step in integration of hybrid television. Until recently, the predominant architectures of hybrid television was that of a bolt-on. You actually took a kind of analog television set and added to that an additional chipset, either on board or on a separate PCB, with set-top box functionality, giving you a hybrid television. That is a perfectly valid architecture when quantities are low, but to be clear to you that with the advance of digital television, especially in Europe, but even more in the United States, where thanks to the ATSC mandate, an entire market was created for us. Thanks for that. Such solutions are no longer cost-effective and not desirable anymore, also from an integrated user experience. So the TV520 actually takes the integration of hybrid television one step further. With one single chipset, you actually can create a hybrid television, a TV520, as you see here. The central PNX8535 processor only needs additional peripherals like RAM and ROM, and a front end to actually make it a complete TV design. To give you an impression actually on the economic pressure on television manufacturers, our key customers, of course. Such an entire small single PCB with all the silicon on it goes actually for prices around $40 nowadays. And that's all you need for an entire television set that you buy at Best Buys or Walmart. Okay, I think that should be sufficient introduction. We address the hybrid television market, and the PNX8535 indeed combines everything that you need for that. So I think it's time to dive somewhat deeper into the leading character of this entire story, the PNX8535 itself. And okay, you see here the use cases and the functionality that is actually incorporated in the device. Well, from the entire storyline, it will be clear to you, it does video decoding for analog, all analog, worldwide analog standards like NTSC, like SPAL, like CCAM, including some of the well-known preprocessor like COM filtering, etc. But it also incorporates an MPEG demultiplexer and an MPEG decoder, HD capable, to deal with all the digital standards that are around there. Together with digital television, you get conditional access. So the PNX8535 actually supports all common open, this is not a vertical market product, all open conditional access systems, like the POT or cable card if you want in the US, and especially the common interface for DVB systems. A television is of course not an isolated device anymore, but it's in fact connected to a plethora of other devices in the home, which means that the PNX8535 is equipped with a host of interfaces and IOs to connect to all these devices like set-top boxes, home theater systems, VCRs, DVD hard disk recorders, but also to your PC and gaming consoles and things like that. So you'll find on there both analog as well as digital interfaces to connect to all these devices, from SCART and Kinches, analog connections, SVS, DVI, HDMI, that kind of interfaces. As I already explained to you, video and audio processing are the key features of any television system. And key to the PNX8535, and a little bit unique to it, is that it actually combines all this together in one device with all the decoding and further interfacing. So there is very extensive video processing in this system, and I will tell you in somewhat more detail about that later. And the same applies actually for the audio processing. The system not only includes all the decoding of all known audio standards, it also implements audio post-processing, like all the virtualization, Dolby type of stuff, SRS, to name a few, algorithms, including all standard stuff like bass enhancements and etc. If you look to the PNX8535, it's a mainstream market device. It actually addresses single window systems, which means no PIP functionality, etc. And it addresses screens up till 3066, 768p at 60 Hertz. Of course, I mean, we have other variants of this device, either in development or near production, that will also address 1080p displays and all that that kind of high-end PIP type of functionality. But the PNX8535 is a single screen system. Its use cases follow directly from that. It can display anything from SD and HD sources connected over any of its interfaces, and at the end it can also play as an FM radio. I think that this will become more tangible if we dwell more into the actual design, if we look in how the system is structured. And one of the major things you have to understand is the PNX8535 is a unified memory system. Actually, there's one central memory system, an external memory controller able to drive DDR1 and DDR2 up till 266 megahertz. That forms the backbone of the system. So we have a very strong internal infrastructure and hub, to call it, that allows all agents in the system, either software agents running on one of the general purpose processors, as well as one of the hardware agents, which are video processing or HDMI inputs, etc. And I think that all by all there are 67 agents on this bus to access that external memory. So in this external memory we store everything from the compressed and decompression data, all the intermediate data of video processing, but also the actual code of the system, data, etc. So it's all stored, and it has been quite an design to actually allow even, it's a 30 bits wide interface and runs at 266, so you can easily calculate you have about 2 point something gigabytes of access. A second, to allow all these agents the sufficient latency and sufficient efficient memory access. If I go over the device, you'll actually see there are two processors in there, a MIPS and one of our multimedia processors, a TM2270. I will say something more on those later. Let me first look at some of the other interesting blocks. I'm not going to go in view of the time into all the blocks, but if you look in there, you will find quite some infrastructure stuff in there. And next to that, you find standard interfaces like I2C, UARTs, GTEx, PCI, the standard stuff that allows, say, consumer electronics manufacturers to support their board design. Of course, you find the television consumer-centric interfaces, like for the conditional access and for the HDMI. And if I then go further, you actually see here to the left, you see the VCP, which is actually the video capture pipe. That's the analog reception pipe, which also includes the decoding of analog standards. The DEMDEC, which is the analog audio standards decoding. And to the right, you see the MPEG demultiplexing and decoding block that allows you for decoding of all the transport streams coming in. Other major points I want to indicate to you is there is a separate audio DSP for the audio processing algorithms in there, and there is a major video processing block through which I will show you later. And we have a separate standby controller, which actually allows for low power behavior of the device. Although this is not a mobile device with its extremely low power standby requirements, also for home devices, it's actually very important to meet Green Star, etc. requirements being in standby. Video processing is, of course, extremely important for television devices. I can tell you that Philips, the different product divisions of Philips, being CE and Semiconductors, have actually built their entire brand position on image processing with names like Natural Motion and Pixel Plus. And the TV520 is not an exception to this rule. I could almost ambiguously say our image is a good image. The PNX8535 actually has very extensive video processing capabilities incorporated in the device. On the screen you now see actually those parts of the device and other representation that are related to the video processing. Is this a pointer? Yeah, okay. To the left of this is again the internal infrastructure with the memory control unit. And to the left you actually see everywhere where video comes into the system, either uncompressed over HDMI or DVI, from analog broadcast, like an NTSC broadcast and is being decoded into the memory, or from a digital broadcast and is being decoded into the memory. So actually, this represents the input side of the device, the input and decoding side of the device. While at the right-hand side, you see the processing that actually takes place on the uncompressed data. Video processing in televisions has gone through an enormous boost in the last year with the introduction of flat displays. You now have a pixel race actually in television with display resolutions up till 1080p. You're already, and 60 Hz displays, you have pixel rates in the order of magnitude of 150 megapixels a second. And that's not even the end of the line. LCD manufacturers are pushing the display and refresh rates towards the 120 Hz, even doubling again that rate, going over the 300 megapixels, and also the bit depth, the dynamic range of those signals is increasing. Did we formerly work with nicely aligned 1 byte pixels? Nowadays 10 and 12 bits. Video processing is actually being the de facto standard. Just the PNX8535 actually processes about 200 megapixels a second. As I said, it's intended for at a 10 bits depth. If I look into the video processing itself, I can indicate a number of blocks. First of all, there is the MBVP, which is a memory-based video processor. It implements functionality like noise reduction, temporal and spatial noise reduction on the images. It implements functions like deinterlacing, as you probably are aware of. A lot of images entering a television device are actually interlaced images. Different images have to be combined to get a real progressive image for the display. That's are rather complex algorithms in which you make use of a number of pictures at the same time, evaluating if this is a still picture, or if this is really an interlaced picture, or if it actually originates from a film. It's a more pull down where they repeat that, the 24 Hertz pictures in 3-2 type of repetition mode, and then forms the relevant progressive picture that is done in here. What is also done in here is actually scaling towards, say, 6 steps, scalars vertical and horizontally to actually allow it to align with the size of the LCD display. We have a composition pipe that actually mixes the video stream with graphics and also adds color features like green enhancement, blue enhancement, tint control, and sharpness features. Actually, there is a second video pipe in the system, but that is meant for what we call the secondary output, to which you can connect your monitor, say a VCR or that kind of recording devices. If you look to the video processing, as I indicated, it's actually built up out of these sub-IPs, which are integrated towards the main infrastructure. Internally, they are built up according to our video streaming architecture, where the different blocks interface to each other in a streaming fashion to, of course, reduce the bandwidth that goes through the memory. I mean, you don't need a pass-through memory after every processing step. For the memory access is actually one of the key parameters of this device, and even though we have quite sufficient bandwidth here for all the use cases, it has been quite a design challenge to keep that under control. Our audio subsystem is quite a similar story. I will not go into as much detail as I did now for the video subsystem, especially since Howard has started waving the red flag already. But But you will find back similar constructions, similar architecture as for the video subsystem. There is a receiving side where actually we have ADCs and decoders to decode the analog audio signals. We have again the digital broadcast. We have HDMI and SPDIF inputs that bring in digital uncompressed data. A Trimedia that actually does the AC3 decoding and other MPEG decodings. And we have a post-processing DSP, a proprietary DSP that brings the data outside and does all the virtualization, bass, tone, and all the other controls. It's quite of the unique features of the PNX8535 that it combines both the audio and the video in one IC. I will speed a little bit up. Just a few remarks. There are two main processors in there, a MIPS MTI 4KEC, which we use to run Linux and all our main application software. And as I already indicated, one of our multimedia devices, the Trimedia TM2270. That is mainly used for audio decoding and a little bit video in this system. However, because of our memory-based solution, we can quite flexibly change these use cases. I will skip this and move on rapidly to the more physical parts of the design, just to give you an impression of what I already said. This is a video processing device, to a large extent. This is the area division on functionality. You see a lot of infrastructure. There's quite some peripherals and IOs, audio processing. As you can see, time's up. Oh, that's more. I jump to my conclusions. You pressed me to have those, so you will not deny me those. I hope that I could convince you that this is indeed a great device. It's one of the highest integrated hybrid television processors in this world, we think. And its most unique part of it is that it combines all the decoding, I/O, and audio and video processing in one device. I thank you for your attention.
Okay, our next speaker is Stephane Mutz. He's the lead architect for set-top boxes and home media devices solutions at Philips Semiconductor. He's been with Philips for 12 years and spent most of his time working on SoC architectures. He holds an engineering degree in microelectronics from École Supérieure, and I cannot pronounce the rest of it. It's ESIEE. Perhaps you can do it for me. Thank you.
École supérieure d'ingénieur en électrotechnique and électronique. That's fine. Thank you. Hello, and thank you for giving me the opportunity to deliver this presentation on heterogeneous multiprocessing applied to video decoding. Let's see how this works. Okay, so in this presentation, I will first start by giving you an overview of the specification of the video decoding solution we have developed at Philips Semis to power our consumer products. I will then proceed to highlight some of the...
Speak louder and clearer.
Okay. I will then proceed to highlight some of the challenges we have faced while developing this solution and give you a view of the solutions we have selected to overcome those issues. And I will end the presentation by giving you some figures and drawing some conclusions. So let's start. This is the charter we have defined for developing the new video decoding solution to power our consumer application products. Those products are mainly focusing on the set-top box and optical storage as well as digital TV market. Therefore, it becomes important nowadays with the advance in these applications to support a number of different standards going beyond the traditional MPEG-2. It's also key to support high definition content as this become more and more available, and at the same time displays are becoming affordable. And finally, playability is a major concern when it comes to consumer applications, as those products have to deal with material coming from many different sources, and those sources are not always fully compliant or error-free. This is the set of standards we have decided to support in this version of the multi-standard video decoder IP. Referred to throughout this presentation as MSVD. Sometimes we are very creative with names. As you can see, the first in line is of course MPEG for advanced video coding, which is becoming very popular for high definition broadcast, as well as IPTV. The same applies for VC1, which you find also in internet streaming. And then you find more traditional codecs, including DV for camcorders and EXIF for still pictures. The IP packs also a few algorithms that are related to removing compression artifacts to give a good quality picture, even for low bitrate transmissions. Oops. Going a bit fast. Oh, the diagram doesn't. There is a problem with the diagram. Too bad. The solution is built around a mixed hardware-software combination that includes an embedded processor dedicated for stream parsing and control. And coupled to that is a hardware accelerator that helps the embedded processor when it comes to bitstream manipulation. And the pixel processing part is handled by an autonomous unit that packs the data crunching units related to the pixel operations like DCTs and motion compensation. And finally, there is a video post-processing unit that takes care of the artifact removal algorithms. So let's look at the rationale behind those choice and the benefit of such an architecture. So we have decided to use a mixed hardware-software solution and rely on an embedded CPU mainly to help in supporting the diversity of standards and their different variants, like the case of DivX, for instance. It's also quite key to help to mature the different decoders to a product level quality, as this is really a challenge due to the sheer number of possibilities when it comes to decoding video content. And this is becoming really a challenge if you would go the hardware way. However, we have decided to rely on to assist the embedded CPU with an hardware accelerator for bitstream manipulation. This is usually not very well supported by processors. And furthermore, it helps to deal with one of the major problems with software, stream parsing, which is the sensitivity to the stream bitrate. And in fact, if you look at the difference between low bitrate streams and high bitrate streams, the difference lies mainly in the number of bits that goes into the residue coding part of the stream. So by offloading that part from the CPU, we can get a very stable performance across all bit rates. And finally, we have decided to use more traditional design techniques for the pixel processing part to deliver high definition performance at affordable cost, but I will come into that later in the presentation. So that's it for the overview. Let's move now to the design challenges and the solutions. I will first start by focusing on the embedded CPU and the control side, and then move to the pixel processing side. So first of all, on the embedded processor side, when it comes to the performance aspect on that side, I think it's important to understand the impact of the latest improvement in encoding efficiency with the last generation codecs. We can identify the three main sources of improvement related to the stream coding as opposed to the pixel processing. They are the following. First of all, standards like MPEG-4 AVC allows for a deeper segmentation of the picture to be encoded, which means that, of course, you have more information to transfer, more symbols to transfer to the decoder. But also, as this segmentation is not uniform, you end up with many cases when it comes to decoding a block as to what can happen at the boundaries. The second point, to limit the impact of this deeper segmentation, the latest standard relies on more sophisticated prediction schemes, which means that you might have more symbols, but most of them you are able to predict from previously transmitted information. However, for the decoder, it means that it also has to reproduce these complex predictions before decoding any symbol. And while previous standards like MPEG-2 only used the previous symbol that was transmitted, codecs like MPEG-4 AVC tends to use a wider set of information, including one coming from the previously transmitted row. So you have to examine not only the block to your left, but also the top left, top and top right, and decide which one you're going to use for any symbol to be decoded. Finally, the third point is the fact that, contrary to MPEG-2, now you could say all the symbols are predicted and not plainly transmitted. So to give an idea, for instance, on motion vectors, comparing MPEG-2 and MPEG-4 AVC, we have about a 50-time increase in the number of operations that it takes before you can really process a motion vector. To be concrete, if we consider MPEG the requirements for decoding a high-definition MPEG-4 AVC stream, let's say we target a 333 MHz processor for that. You end up with a budget of roughly 1,350 cycles per macro block. If we now consider that this is a high bit rate streams, meaning that half of the transform coefficients are coded into the stream, that means that you have roughly 6 cycles to process each symbol. If we look at the impact of the use of more prediction and context information, there is also a huge impact on the data manipulation and context information you need to load and store, resulting in about 700 load and store operations, not just talking about the main symbols, the macro block type and the motion vector, excluding the storing of the residue themselves. And finally, due to the high complexity of the coding scheme, the process has about 100 different branches, so it's very sequential and very difficult to exploit parallelism there. However, it's necessary because you could not do that with traditional general purpose RISC CPU. So we have decided to apply one of our VLIW media processor for this task by deriving a configurable processor core from the Trimedia architecture. So this core is running at 333 MHz. It has 5 issue slots. 35 functional units and a 9-stage pipeline. But its characteristics goes beyond that. There are three main specific characteristics about this core. We have added a specific coprocessor interface on top of the traditional BIU to have a better interface, a better communication with the external hardware coprocessor. We also have make use of user-defined functional units so that we can add some application-specific instructions to the core. And finally, we use a parallel load and store unit, which means that you can issue a load and a store in a single cycle, and that helps a lot to deal with the number of data transfer that you need to do for the context manipulation. I don't know, but when we view the slide, I think we have lost all the diagrams. So let's go into the two specific aspects. The coprocessor BIU. Why do that? Basically, it is important to have a low latency connection when you want to use a hardware coprocessor. Otherwise, all the benefits you might get from having a specialized engine might be lost in the communication. In our case, we have used this processor for operations like read bits, skip bits, but also a number of variable length decoding operation, as well as support for Kabak decoding at the symbol level. This is viewed by the programmer still as a load store interface, making it very easy to program. But the good thing is that there is a direct compiler and scheduler support for this interface, and you can adjust the latency for the load and store operation on this interface, which enable the scheduler to optimally schedule the access and the use of the results coming from the hardware accelerator for the rest of the processing. This alone, compared to connecting a standard connection BIU interface, has brought a 15% performance improvement in the stream parsing section. So the other thing we have put to good use is the user-defined unit. This is basically an SIMD capable functional unit that you can tailor for specific application needs. This is quite powerful for an embedded CPU because you don't care so much about specializing the unit for a certain application. We have reaped the following benefits from this unit. We have increased the parallelism of some operations. For instance, motion processing. We can process the X and Y coordinates in one go. But the main benefit has come from the possibility to put complex operations, including tests and computation in one go. This has yielded a very good impact on performance by removing all the low-level branches from the program, which were inhibiting the capability of the scheduler to really exploit the 5-issue slot machine. And it also helps to get rid of the branch latency in that case. So that's it for the CPU, for the embedded processor part. Let's now look into the pixel processing part and what we have done specifically here. I start that part by showing an overview of the MPEG-2 coding scheme on the top of this slide, and the MPEG-4 AVC coding scheme on the bottom. As you can see from a distance, the schemes are very similar. They are built around an intra-coding, what we call the intra-coding path, which directly encode the pixels by transferring them into the frequency domain and then applying quantization to control the amount of information. And motion prediction compensation pass that recovers data from neighboring pictures to limit the number of pixels that needs to be transmitted. So based on the fact that that you find a similar structure between the different compression schemes, it becomes possible to build a pixel processing unit for decoding the pixels by exploiting this structure. So this was our initial view of the processing unit based on the hardware design solution. You find on the top side the different units that are linked to the intra-coding path, so the inverse quantization and the different version of inverse transforms that you need for the different coding schemes. And on the bottom, you find the motion compensation units. However, what is relatively easy on the motion compensation side that is to merge the different requirements from the different coding schemes into a limited set of units proves to be a bigger challenge when it comes to the intra-coding path, because you have really a diversity of transforms there. MPEG-2 is using a discrete cosine transform. DV does the same, but with different shapes. But when you move to MPEG-4 AVC, you find an integer transform, which is again different from the VC1 one. So, sticking to hardware there has some drawbacks. Because you basically end up in the situation where you either put multiple instances of transform units dedicated to each of the standards you want to support, but that costs, that's quite easy to design, but that costs area. You could also think about merging everything into a super duper hardware unit, but the verification is going to be a challenge. And when fixing things on one side, you might run the risk of breaking things then. So you could also think about using symmetric multiprocessing, but that's usually end up to be costly and not so optimal. Scheduling is also a challenge with latest standards. So for that, we have decided to go through another way and use application-specific processors. If we focus on the transform side, when you go one step further and look at the different transforms, what you see is that basically they are all 2D block operation achieved by applying a 1D transform sequentially in an horizontal and vertical path, and they are all butterfly-based operations. So basically, we have defined a dedicated processor that is able to support that efficiently. This is the view of the pipeline. So beyond the traditional instruction fetch and decode stage, the unique characteristic of this processor is the introduction of an operand fetch stage and a write back stage that give direct access to the buffers. We also went to dual issue to meet the performance target. So this processor achieved the following performance by relying on the load and compute and and store operations. We are able to do a 1D DCT in 7 cycles, which means that we can process an HD MPEG-2 stream at speed by processing macro blocks in a bit less than 700 cycles. And the same processor performs quite well on the MPEG-4 AVC transform with 16 cycles for a 4x4 transform. Area-wise, this is also very competitive against hardware units, and it proved to be very easy to design and support the different standards. So We are also then decided to apply the same approach for deblocking, especially VC1. We already had developed hardware for MPEG-4 AVC deblocking. It was quite painful. So based on the benefiting from the programmable aspect of a dedicated processor, we have decided to design one that would help in mapping the control and the data access for deblocking into firmware. For this one, we have used a slightly different structure with a pipeline ALU for the filter operation. The filter operation is fixed, so it's only good for a very specific deblocking algorithm, but the design time was reduced by 2 times compared to developing a hardware state machine for that. So let's conclude with some figures. The multi-standard video decoder IP has been developed in 90 nanometer low process technology. The embedded VLIW configurable processor is 3.2 square millimeter big and is running at 333 megahertz. The rest of the logic, including the ASIPs, is 3.7 square millimeter and running at half the speed. Total area is a bit less than 7 square millimeter. So in conclusion, I think heterogeneous multiprocessing has proved to be very efficient in this application. Relying on different type of processors and using ASIPs has brought at the same time a great deal of flexibility, helped a lot with the design time and risks. And deliver a very affordable solution for our products. Thank you. Thank you.
All right, the next and last paper in this session, we have 2 presenters, Marcin Klecha and Ralf Karge. Marcin received his master's degree in electronics from the University of Gdansk, Poland. He worked at Philippe Semiconductor, Eindhoven, on the architecture and design of multiple SoCs for portable and mobile multimedia applications. Currently, Marcin is working as a system architect at Philips Semiconductor Advanced Systems Laboratory, focusing on applications using the Nexperia-based platforms. And Ralf got his degree in computer science at the University of Applied Science in Hamburg and is currently managing the software team at the Trimedia Center of Excellence in San Jose. So I don't know which one is first. Is it Marcin? Well, you're both first. Okay.
I was supposed to check microphones? Yes, it works. Good morning. So with the last presentation before the break, we would like to change the focus of the discussed topics from home and stationary devices to more the mobile solutions. Before, we would like to introduce you to the PNX4103, the Philips Nexperia mobile multimedia processor. Even though it has been designed for mobile and portable devices, it promises to deliver performance equal to that known in the home and stationary devices. Let me start with acknowledging the entire PNX4103 team that consists of more than 100 engineers and with the design teams that were spread all over the world. Content-wise, we start with a brief description of the requirements for the next generation mobile phones. Then we present a system architecture of the proposed solution. In more details, we dive into the video engine and imaging processor. We mention the power management framework and the power management solutions. And of course, it would not be hot chip presentation if we didn't mention silicon characteristics. Let me start with asking you a few questions. I promise not too difficult. I know it's still pretty early. So would you use your mobile phone as the only camera at your daughter's wedding? Would you use your mobile phone to download a movie, connect to your beautiful, huge LCD TV, and invite your friends over for viewing? Would you use your mobile phone to record the World Cup finals? The next soccer finals are 2010, so you still have time. I'm not going to ask all of you for answers. Personally, I would have to say no to all of those questions. Especially when I look at the mobile phones that I carry with me, I have my pocket, still fits. But we do think that having such features on the mobile phones, it's a really cool thing. Therefore, we set such standards for the next generation mobile phone platforms. Some of you have probably seen the Mama Shrunk the Kids movie with a very nice device to actually shrink everything surrounding you. And I wish we had a similar device when designing the next generation mobile phones. TV on mobile, navigation, video conferencing, high definition video decoding. Well, requirements for the next generation mobile phones, it's actually like shrinking your entire living room or car entertainment system, including a digital camera altogether, and squeezing it all into one device. So how to squeeze it into such a device without significantly increasing the overall power consumption? Well, with the PNX4103, we don't want to address all of those problems. Instead, we'd like to focus on the multimedia part of the mobile phone. PNX4103, it has been designed as a video coprocessor. Therefore, it assumes the presence of an application processor in the system. Application processor controls the PNX4103. It is also responsible for controlling your user interface, access to the storage, or to the connectivity. So PNX4103 interfaces to such an application processor via a standard parallel interface with a speed reaching up to 400 megabits per second. And that's a speed that allows us to achieve and realize all the targeted use cases. On the rendering side, the main display is a RAM-less LCD display with the resolution up to wide VGA, 800 by 480. A RAM-based display, quad VGA. And next to the local displays, it is also capable of displaying content on a TV. So there is an analog output straight to your TV or DVD recorder that is capable of supporting both PAL and NTSC. It does also support dual camera sensors that could be either a CMOS sensor or a CCD sensor. And another interesting part is the die stacking memory included in the package, but I will talk about this later. So let's zoom into the PNX4103 itself. PNX4103, it's following Philippe's platform approach based on dual core architecture. As the control processor, you can consider this as the left part of the brain. The PNX4103 utilizes ARM 926 processor with 32K caches, both for instruction and for the data. The control processor can run up to 208 megahertz. We wouldn't like this to run so fast. We try to keep it as low as possible, but that's the maximum speed that it can achieve. It interfaces to a system bus that can run at up to 104 megahertz. That then goes to the main memory that can run at 133 megahertz. Already mentioned LCD outputs and TV out. are supported by hardware renderers that are responsible for scaling, for rendering of graphics and video, for format conversion, etc. But that's not exactly what we would like to focus on in this presentation. Instead, we would like to explore the right side of the brain, which is video engine, Philippe's Trimedia, TM3270, as well as the imaging processor.
So you've heard about Trimedias in the previous presentations already, all targeting stationary consumer applications. For this product, we had to come up with a new, more powerful family member. And one of the main objectives was to provide a programmable, multi-purpose solution capable of encoding and decoding H.264 standard definition. It also should run our proprietary video enhancement algorithms much more efficiently. Yet, it had to be suitable for the battery-operated devices. For the stationary consumer devices, low operating power is mainly considered a nice-to-have feature. It can help you keep your electricity bills low or help California avoid rolling blackouts. Yet for battery-operated devices, low power is imperative. So the target that we had here was to come up with a solution that provides sufficient programmable performance at acceptable power in the smallest possible silicon area. Thank you. So what did we come up with? The TM3270, you see it here in a nutshell. It's a 5-issue slot, 32-bit VLIW core implemented as a fully synthesizable design using off-the-shelf SRAM memories in 90 nanometers low power process technology. All of its the operations in all of its 5-issue slots can be guarded by one of the 128 registers. And the pipeline is 7 stages deep for single latency operations, and it goes up to 5 stages. The large data cache of the TM3270 is optimized for video processing of standard definition. You can see that on the floor plan there that the data cache, along with the 64 kilobyte of iCache, account for about half of the total course area. Next slide. So, that I missed. So what are the essential features in the TM3270 architecture? One important aspect, of course, is the extension of our instruction set architecture. We have newly introduced the 2-slot or super operations in the TM3270. They are executed by functional units of neighboring issue slots, allowing for up to 4 source operands and 2 destination operands. To reduce the load of motion estimation kernels, we've added fractional loads. These loads combine the functionality of a load with a linear on-the-fly filtering of the pixels, allowing for very efficient implementations of fractional pixel calculations. I'll say a little bit more about the H.264 operations later, but as you probably all know, instruction set extensions by themselves are of little value if you don't have sufficient ways of getting and storing the data to be processed. So I just want to mention 2 of the relevant features here. Our hardware prefetch approach is based on memory regions. It allows you to define prefetch patterns that match the data patterns, the access pattern of data structures in memory. When the processor performs a load on an address in one of those regions, it'll issue a prefetch request for the address plus a programmable stride to the prefetch unit if that new address is not already included in the cache. Additionally, our allocate on write miss policy reduces the miss penalty in the cache. You might have seen on the previous slide these data valid blocks. They are used to indicate the validity of each byte in a cache line. And they keep track so that when a cache line is copied back to memory, only bytes that are actually validated get copied back. This reduces the bandwidth to the off-chip memory and also the power consumption. Another relevant aspect for reducing the power consumption is clock gating. This design is heavily clock gated. We've actually implemented 170 separate clock domains. Just as an example, all stages and all functional units are gated separately. So only the operation that is, so if a stage is not used, it's actually not clocked. Let me give you one example of an instruction set operation that is video specific. The processing of median values is very important for most pixel improvement algorithms. This example here shows a 3 taps median of 3 8-bit pixels which get stored in an image. It's a rather trivial calculation, and the problem with that is that as we do video processing, we have to do this over and over again for all pictures in an image. So in order to speed this up, we've introduced a new super operation which allows calculating 4 of those median values in one run. So it processes all 4 median values. It requires 2 issue slots, but it's much faster than doing 4 separate calculations. I'd mentioned before that being able to decode H.264 standard definition and encode is a strong requirement. So while we try to keep the instruction set very versatile, we identified that the Karge processing is a big part of the overall computational power that is required for the H.264 decoding. It's not possible to implement this in an efficient way on our SIMD VLIW architecture. So in order to speed this up, we were trying to identify new operations. Ideally, we would have liked a single operation that matches or implements the binary decode symbol function of the H.264 reference. But because of the large number of input and outputs, this is not possible on our architecture, even with the new super operations. So nevertheless, we found an alternative that by grouping some of the arguments into a 32-bit operand, we could actually come up with a solution that requires no more than 2 operations. So you could group the value, the context-related values, the value and the range, into one 32-bit operand, and we could also group the state and the MPS into 32-bit. This way, we came up with 2 new operations for Karge processing that sped up the Karge processing on our processor by a factor of 1.5 to 1.7. And as you can see in the measurements on the right, it actually helped us to well meet the target of decoding H.264. So, of course, the target could also have been met with dedicated hardware. Why did we go for a programmable solution? Well, mainly, we want to use the processing power of the Trimedia for a wide range of applications and not just for decoding. As Marcin had already pointed out before, video processing at home entertainment quality level will soon be a must for even mobile devices. Let me give you one example. DVB-H is a standard that operators will use to transmit video data. They will actually use class B of DVB-H, meaning 15 frames per second, SIF resolution at about 384 kilobits per second. The operators, however, would like the end users to get a much better experience in viewing those video images later. So they want video enhancements. The advantage of the TM3270 is that for those lower resolution H.264 streams, we only need a small part of the overall processing power, thus allowing us or giving us headroom for additional video improvement algorithms. One concrete example in this context is mobile natural motion, or also called frame doubler. It uses motion estimation and motion compensated temporal up conversion to get to a smooth display of 30 frames per second. On the slide here you see a similar example from 12 to 24 frames. That's what we had implemented as a demonstrator in our lab before. So it actually turns out to be a very nice balance between the load for video decoding and the availability of cycles for video processing. If you have high quality video coming in, it requires most of the CPU cycles and you need to do little improvements. If you have low quality video coming in, you need little cycles and have much headroom for video algorithms. Using the Multimedia in that context also allows us to reuse a large part of the algorithms that had been developed in the TV and consumer application space. So that mobile natural motion is actually something that came out of software natural motion for a TV. Other application spaces are also encoding, and now Marcin will take over again and explain the imaging processor, which is used to capture the encoded material.
That's right. So before you start encoding, you have to capture your content, and that's the responsibility of your imaging processor block. As already mentioned, it supports dual camera inputs, so high resolution one with the resolution up to 10 megapixels, and the secondary one with resolution up to D1. Not only two cameras, but also two processing pipelines are supported, so you can process those two cameras simultaneously for certain use cases. Just to name a couple of interesting blocks in the processor. Enhanced camera signal processing block. You find one here and the second one here for the high and low resolution. First of all, responsible for transforming raw RGB into the more formalized YUV444 and RGB. Signal processing functions, but also it incorporates an embedded measurement engine. That measurement engine allows you to implement such algorithms like auto white balancing, auto focusing, for example. Another interesting blocks that allow you to ease the encoding is noise reduction block. It's a special filter that allows you to achieve better compression by removing the noise from your signal. Jitter extraction block. Jitter extraction block is used in the image stabilization algorithm. It allows to calculate the jitter between two frames. So it produces the global motion vector. It is a streaming architecture, so you don't have to go to the memory with each of the block outputs. Instead, you can send data from one block to the other. Like, for example, camera signal processing block can send data directly to your JPEG encoder. It is streaming based, but it's also very scalable. The blocks connect together via DVDO matrix. The matrix that can be programmed, so you can freely choose what is the exact data path. And you can choose to either skip, for example, JPEG encoder or do it on the fly. At the connection to the matrix, there is also frequency domain crossing. So it allows you to choose the frequency of each of the block depending on the use case. And that's an excellent power management feature. Allows you to reduce the power consumption for the low resolution content. The clock scaling in the imaging processor is not the only features, low power features supported by the design. From the general principles, the 4103 is using high VT transistor cells that allows you to achieve lower standby power consumption. On the design level, the central clock generation unit with over 100 independent controllable clocks allows you to tune the frequency, again, depending on the use cases, allows you to remove a frequency from a certain IP block. Next to this, you have also auto-gating in many of the blocks. So without going to the CGU block, the block detects whether it's being used or not, and it can switch off the frequency by itself. The Trimedia has been designed in a standard VT, so that actually increased the leakage, but allows us to achieve 350 megahertz in the worst case, and even going to 450. But we do control the leakage by applying a separate voltage domain to this area. So independently from the rest of the system, you can remove the power as well as the leakage. Another power management feature of the Trimedia is partial power down of the core and the full power down of the IC. Next to the frequency scaling, we can also apply dynamic voltage scaling. So those were just design hooks offered by the PNX 4103, but you have to enable them in your system in order to make use of it. So this is a power management framework. The functionality, that's a software view, so no hard blocks anymore. The functionality of the PNX 4103, it's exposed to the application processor via a host API. And via this host API, the application processor can, for example, switch on and off the external device, like a camera, by issuing a command start and stop of the camera that is then understood by another driver that sends the appropriate I2C commands. The application processor can also set the system in one of the power modes that is then understood by the global power manager. Global power manager, it's a small driver that runs on the ARM processor. And depending on the set mode, it can set also the right parameters of the clock, but also it can set the right voltage. Internally, the ARM and Trimedia can also control its power consumption. Just to give you an example, on both ARM and Trimedia, we use so-called idle process. The idle process is being scheduled on the operating system when there is nothing to do. And based on that, the processor can decide to go into one of the standby modes. So that brings us to the silicon characteristics. Do I have the right card yet? It has been designed in a low power CMOS 90 millimeters process, and it operates at 1.2 volts. It says it's a small 10. Is it over? No.
No, just continue.
No, it's okay.
Microphone going up?
Yeah.
Why don't you use the mic at the podium?
No, it's okay. So it's 10 by 10 millimeters package. Over here you have the floor plan of the IC. In the upper left corner, that's Trimedia. And we have left enough clues in the presentation for you to estimate the overall digital die area. Typical power consumption. I state here 1 milliwatt per megahertz for Trimedia, but that means that this is for a fully loaded processor. Fully loaded. As Ralf explained, the Trimedia core is heavily gated. So if there's nothing to do, or you have processor stalls, the clock gating kicks in, and then this number goes down. So it's very difficult to say what the power consumption is unless you know exactly what is the exact number of cycles and operations per instruction. Oops. Another interesting feature of the IC is die stacking memory. We have 128 megabit die stack low power DDR. That allows us, first of all, to reduce the size of the entire solution, but also to reduce the power consumption, since we do not have to go high voltage to the off-chip memories. 128 megabits is the size that allows us to perform all the standard definition video decoding. That brings me to the conclusions. So PNX 4103 is based on a dual core architecture. Low power implementation of the Trimedia DSP allows us to achieve the home entertainment quality multimedia on the mobile and portable devices. And programmable design offers system upgradability and flexibility in, for example, new algorithms like natural motion. The additional imaging processor block allows you to get rid of your additional camera in your packet, and that allows to achieve the high quality video recording and still images. The die-stacked memories for a smaller footprint, and design as a coprocessor allows you in an easy way upgrade your current design by applying this solution. I would almost forget about this one. So I hope that once you come across a device with 4103 inside, you will be able to answer yes to all of these questions, and you'll be able to enjoy your mobile phone even better.
Was there a question?
Oh, there was a question?
Yeah. I think so.
So
No break yet, sorry.
Hey, Marcel Sierra with Intervision. Early in the talk, you mentioned that there's pressure to go to 10 and 12 bits in the pixel, with the pixels. And, but in some of the processors, you are dealing with 8-bit pixels. With the dynamic range of film still being better than digital, how far along do you think it is that we're going to be seeing TV monitors all go to a 10 to 12-bit standard for this capability?
It's not really a mobile question, but more specifically video processing overall. And there the trend for sure goes towards 10-bit displays. We've identified that most of the video processing, the underlying, can actually still be done in 8-bit, but then you have intelligent ways to convert and merge that data again to get 10-bit quality. So it's not a reason not to support 8-bit anymore.
And what happens into the dynamic range of, say, an input camera that actually can provide 10 bits at some point? How does that get preserved?
The input camera, it has 10 bits. The input camera, it is 10 bits. So the display indeed, it's 8-bit processing, but the image camera is actually 10 bits.
It's already the interface, the current interface
already
for
the current. That's right. So the current interface. So,
Thank you.